You did not pick this video. The YouTube algorithm did. And right now, it's deciding what billions of people will watch next, including you. But it's not just YouTube. Recommendation algorithms are constantly predicting your next move in nearly all aspects of your life. They choose your music, the ads you see, the products you buy, and even who you might date. Today, we'll pull back the curtain on how they work and how they're about to get so much better. Hi, I'm Dan. I work on recommendation and ranking systems in big tech. And today, I'll be explaining recommender systems, what they are, how they work, and how they're evolving in 2025 with the advent of generative AI. No machine learning knowledge required. Quick note, I do not work at Google or YouTube. Everything described in this video is publicly available and comes from a mixture of my own experience, industry write-ups, and academic research papers. So what are recommendation algorithms? Well, simply put, they're a method of showing the user content they're likely to engage with based on that user's past behavior. But why do they exist? To answer that question, let's go back to the internet circa the mid-2000s. At that time, as the number of internet users was quickly growing, so too was the total user base on many of the new and virally growing social media companies like Twitter, Facebook, and of course, YouTube. Feeds were overflowing with content. Ad dollars were their business model, and all of them were wrestling with two questions. One, how do we keep users on our platform, as more time spent on the platform equals more ads, which equals more revenue? And two, how do we curate the right content towards the right user? Recommender systems would eventually provide the solution here. But at the time, with AI and deep learning being a far cry from where they are now, these algorithms were relegated to niche academic circles. That was until October 2006, when Netflix announced the Netflix Prize, a $1 million award to any developer who could beat their movie rating predicting algorithm, Cinematch. The competition ran until 2009, when Belcour's pragmatic chaos algorithm finally beat Netflix's Cinematch. Ironically, the winning algorithm was never actually adopted by Netflix, as the solution posed by the winning algorithm was way too complex for the now new streaming service that Netflix was providing. However, even though none of the submissions were actually used, this competition had wide-reaching impacts on the industry as a whole in three key ways. One, it mainstreamed the field of recommender systems, moving it from a niche academic field to a mainstay in the industry, and popularizing certain algorithms like matrix factorization and collaborative filtering, both of which became mainstays and foundations for many big breakthroughs in the field of recommender systems in years to come. Two, it shifted the main focus of the field from modeling and predicting explicit feedback like user ratings to predicting implicit feedback like clicks, watch time, and video skips, which are much better proxies for predicting user engagement than actual movie ratings. And three, it created a standardized benchmark for researchers, as the dataset Netflix released for the competition Movie Lens became a key benchmark that would guide research in this field for the next 1.5 decades. By the early 2010s, most big tech platforms had some sort of recommendation system, but it was really around 2016 and 2017, with the widespread adoption of deep neural networks, that these algorithms began to feel truly personal. Today, recommendation systems are everywhere, virtually powering some of the biggest websites on the internet. They're quite powerful, and with the rise of Gen AI, they're getting a lot better fast. On YouTube, over 70% of watch time comes from recommendations. On Netflix, more than 80% of views are driven by the algorithm, not search. On Spotify, Discover Weekly alone generates hundreds of millions of streams each week. On Amazon, personalized recommendations account for roughly 35% of total sales. And on platforms like Hinge and Tinder, millions of people are matched every day by these recommender systems. Given how much of our online life runs on these systems, understanding them isn't just important. It's essential. Before we move on, I want to throw it back at you. Which platform do you feel understands you best? Is it Spotify, TikTok, YouTube, or some other platform? Let me know in the comments below. So we established that recommender systems are everywhere, but how do they actually work at scale? To make it concrete, let's look at the YouTube algorithm as a case study. The YouTube algorithm has two main jobs. One, the home feed recommendation, what a user sees when they enter YouTube. And two, up next recommendations, what plays after each video. In both cases, the system must, for each user, in real time, pick the topmost handful of videos that user is most likely to watch next, choosing from billions of possible videos and returning the top 50 or so most likely results. Our goal is to create a system that can do just that. When you open YouTube, the client, aka the browser or app, asks the YouTube backend server for data. The server then queries the recommendation system, whose job it is to select those top 50 or so videos for you. To handle this at scale efficiently, recommender systems run in multiple stages, each stage filtering out several videos until only the top handful of videos remain and are returned to you. For simplicity, think of it in two main stages. The first is candidate generation, where the algorithm quickly selects the top 10 to 20,000 videos that are most relevant to that user. The second stage is ranking, where powerful models score each of the candidates and return the top handful or so videos to the user. Behind the scenes, each stage is making heavy use of caching, so the algorithm does not have to do all this heavy lifting every time you refresh YouTube. Let's start with the candidate generation stage, also called the retrieval stage. The goal here is to quickly narrow down the pool of possible candidates from billions of videos down to a few thousand. As an analogy, we could think of video recommendations to be kind of like casting for a reality TV show, like say Survivor. In this analogy, the candidate generation stage would be like casting directors reviewing audition tapes and resumes and deciding which candidate is worth coming back for a real proper audition where more scrutiny will be applied to the candidates. In other words, the goal of the stage is not to pick the best of the best, but to narrow down the pool to a much more manageable size while being careful not to discard the best candidates. The candidate generation stage consists of the following: simple rules-based filters to drop a majority of irrelevant videos. For example, if I only ever watched English-speaking videos, it'll likely drop all non-English videos. The same happens with videos that have been shadow banned, aka not allowed to be recommended for one reason or another. Simple lookups that correlate users' interests and likes with videos whose topics fit into those categories or adjacent categories. For example, if I had never watched makeup videos, I probably would have most of them filtered out. And finally, simple ML algorithms like k-nearest neighbors, where the algorithm uses small pre-computed embeddings, which are compact numeric representations of users and videos, to find videos that have similar content to what the user has watched before. Now that we have our top few thousand candidates, let's move on to the ranking stages. Yes, there's usually more than one. Going back to our reality TV analogy, think of the ranking stages as the actual auditions, where people come in and casting directors scrutinize their performance, where each audition gets longer and longer and more attention is paid to each candidate as the process goes on. The ranking stage employs several powerful machine learning models. The goal of these models is to predict your behavior, be it watch time, likes, clicks, comments, etc. We'll talk about how these models learn soon enough, but when making their predictions, each model takes in a set of features that can fit into three categories. User features, including history, preferences, device, and region. Video features, including topic, freshness, engagement statistics, etc. And context features, time of day, session length, etc. These models then spit out their prediction in the form of a probability for what they think your behavior might look like. All these model probabilities are then passed into a formula called the utility function, which is a weighted average of sorts that determines the final ranking score. An example utility function could look like this. The final score equals alpha times the predicted watch time plus beta times the probability of like, and so on and so forth. Where in this case, alpha, beta, and gamma are weights that reflect platform priorities set and tuned by machine learning engineers through running various experiments and A/B tests on their platforms. The highest scoring videos get sent back to you. But how do these models learn to predict your behavior? At a high level, any ML model learns by comparing its predictions to reality and then adjusting its internal parameters. It takes input data X, produces a prediction Y star, compares it to the true label Y, and tweaks its weights to reduce error, repeating this millions of times. For recommender systems, the training data comes from user interactions, which include every impression, click, and watch event. Each of those becomes a labeled example. For example, did a user click on a video when it was shown to them? If so, then the label for that click is 1. If not, then it's 0. Also, continuous labels like watch time are just recorded as is. So yes, when people say that the YouTube algorithm is learning from you, what they really mean is that every view, skip, like, or replay gets recorded into YouTube's dataset, which is then used to train future versions of their recommendation models, thus updating the YouTube algorithm. Modern recommendation models use large deep neural networks, often built in a two-tower architecture. One tower learns a user embedding, a vector representing your interests based on past behavior. The other tower learns an item embedding, a vector representing each video and its audience. The model then compares these embeddings to predict how strongly you'll engage with each video. Over time, with every interaction, the system gets better at figuring out who to recommend each video to. But what if you are a new user on YouTube with no watch history to speak of? Or what if you just uploaded a new video that has not been watched yet? How would the algorithm know who to recommend your new video to? Well, in the world of recommender systems, this is what's known as the Coldstart Problem, or the problem of recommending new users and content when no data exists about them. Well, for new videos, one way that YouTube gets around this problem is by testing the waters. YouTube shows your new video to small targeted groups, starting with your subscribers and to users who watch similar creators. If that initial audience clicks, watches, and engages, then those positive signals become training data. The algorithm now has positive examples, so it can now recommend this video to a wider audience. This is actually why big channels are always cautioned against making videos that might not fit their current audience. Since if their subscribers don't engage with this video, then the algorithm might flag it as not being worth recommending to other people. Of course, this isn't unique to YouTube. Virtually every big tech platform, be it TikTok, Amazon, Netflix, Spotify, run the same logic, predicting what you do next and optimizing for it. These systems don't just reflect our preferences, they shape them. The feedback loop between you and the model continuously amplifies what works, creating a digital ecosystem that feels very personal, yet strangely predictable. For years, these systems relied on specialized models, each predicting one metric, whether you'll click, how long you'll watch, or if you'll return to the platform tomorrow. But that's all starting to change. As of 2025, a new wave of algorithms are emerging, ones that combine everything into a single model that learns faster, adapts quicker, and understands you more completely than ever before. Let's see what that future actually looks like. Thanks to two major breakthroughs, the next generation of recommender systems are becoming a lot more capable of understanding both us and the content they recommend to us. The first of which is a trend towards what's called multitask learning. Instead of maintaining separate models for every prediction, click, watch time, satisfaction, etc., companies are merging them into one model that learns all objectives jointly. Closely related is multi-scenario modeling. Traditionally, different use cases, for example, Netflix's search versus homepage, or YouTube's up next versus home feed, each require distinct ranking systems. Now, modern multitask architectures are becoming capable of handling all these contexts within a single model, sharing information across them for faster adaptation and better personalization. The second shift is the rise of large multimodal models and generative AI. One application of using Gen AI is to actually address the Coldstart problem for new users. For example, Amazon researchers recently found that generating synthetic watch histories based on similar users' interests for new users can dramatically improve recommendations. Even more interesting, some teams are starting to model user behavior like a language model. Just as an LLM predicts the next word in a sentence, these systems predict the next video, treating each piece of content as a token called a semantic ID. YouTube Shorts and similar platforms already use this approach to track rapidly changing user interests month to month. Both trends actually culminated in a breakthrough this September when Chinese short-form video platform Kuaishou published a paper called OneRec. In it, the authors propose replacing the entire multi-stage pipeline with a single massive model, similar in spirit to ChatGPT, that predicts what a user will watch next. OneRec deserves a whole video on its own, but in short, instead of using separate retrieval and ranking stages, models the entire recommendation process as one sequence-to-sequence task. It encodes users' past behavior, predicts the next likely videos, where videos are represented by these previously mentioned semantic IDs, and fine-tunes the output using a reinforcement learning technique not too different from the technique that OpenAI used to make ChatGPT so user-friendly. This fine-tuning aligns recommendations with what users actually want to see. OneRec is a glimpse of where all recommender systems might be heading. Giant, generative models that don't just predict how you'll respond to each video, but anticipates what exactly you'll watch next. Would you want a system like that curating your feed? Something that knows you so well, it can directly predict what you'll do next? Does that sound exciting or a little unsettling? Let me know in the comments below. Recommender systems start as simple math, trying to predict what movies you'd rate 5 stars. Today, they're the invisible hand that guide virtually every one of our interactions on the internet. And with models like OneRec, they're becoming even more powerful. Systems that don't just predict our behavior, but generate it. So the next time you click on a video that feels perfectly picked for you, it probably was. The real question is, what's really choosing what you watch? You or the algorithm? If you enjoyed this video in any way, then I'd love it if you subscribed. And if there's anything from this video that was unclear to you, or if there's any topic that you would like me to cover next, then do please leave a comment down below. I'll reply to every single one of them. Otherwise, thank you so much for watching, and I'll see you in the next one.